very much. Thank you very much for this introduction, and thank you for the invitation. It's a great pleasure to be here. What I'm going to talk about is based on joint work with Shirikyan and two other collaborators, Evans-Searles, who is now in New York University in Shanghai, and Claude Montpellier, who is a long-term collaborator of Shirikyan and also mine yes, from Central for Physics in Marseille. But actually, my talk will be mostly about this subject, Gallavotti-Cohen fluctuation principle, and I will use a very simple example to tell you what all this stuff is about. And only closer to the end, I will talk about our joint work with these collaborators and our contribution, and finally about some open problems. So here is the plan of. Okay. So this is the plan of my talk. I will begin with a very short introduction, which is basically some citation from work of Leibniz. And he talks about Boltzmann entropy and probabilistic point of view about the evolution of the Boltzmann entropy. Then I will introduce the model on which I'm going to describe all the results of the theory. After that, I will deal with a precise formulation of the result. And the main point is that everything is reduced to our deviation principle. Once you have that, you will have what I call the Gallavotti-Cohen fluctuation relation. And I will tell you about the law of that principle with the relation of that principle with the second law of thermodynamics. And finally, last 15 minutes will be about risk of three flows. And we'll talk about our results in this subject. Okay, let us start with this with the question asked by Leibniz in a paper published in '93. He writes that all microscopic physical laws are time reversible. Nevertheless, there are quantities like Boltzmann entropy, which has preferred direction of time. And he will describe this concept and explain why there is no contradiction between these two observations. On the one hand, you have reversible physical laws. On the other hand, you have preferred direction of time for the entropy. The Boltzmann entropy is not the subject of this talk, so I won't talk about it, but it is important discovery, and it is even mentioned in the gravestone, on the gravestone of Boltzmann in Vienna. I will talk about Leibniz's description of Leibniz justification of this observation. Besides two papers, besides two books, one physicist, Richard Feynman, and the other mathematician, and both of them give more or less similar justification for the existence of preferred direction of time. We will write that it is the point is that the initial state is so improbable that you will never return to the initial state, and therefore you will never get the same value of entropy, whatever it means, without specifying what entropy means. You will never get the same value of entropy as you had in the beginning of the observation. And Feynman writes a very similar thing. He says that although in principle you can go in the opposite direction, but the probability is so small that it doesn't happen in a million years. So for instance, he gives the example of a mixture of ink and water, and says that no way the two you will see them to separate from each other. The Leibniz paper was published in '93, and within 2 years after publication of the paper, Evans-Searles and Gallavotti-Cohen discovered a new law of non-equilibrium statistical mechanics, which gives quantitative characterization of this impossibility. It says that going in one direction is much more probable than going in the opposite direction. What does it mean it's much more probable? Is it possible to give any numbers in the theory? And what I'm going to tell you about in the next two sections is that it is possible, following the work Evans-Searles and Gallavotti-Cohen, in fact, further developed by many other authors. I will mention it a bit later. Okay, so now the model. So we'll be discussing finite state Markov chain. So let us denote by psi k a homogeneous Markov chain, which can take only finite in any state. So I index the state by integers from 1 to L, assuming always that L is greater than 2, greater than or equal to 2 to avoid trivialities. And I assume that this homogeneous Markov chain is described by the transition matrix Pij. I wrote the indices here rather than in subscript to avoid multiple subscripts later. So this means in particular that if you fix the state of the chain at time k, let's suppose that is equal to I, then the probability that at time k plus 1 is equal to j, it is in the state j, is exactly given by the entries of this matrix, Pij. So this is true for any ij in the phase space and for any k. And in particular, there is no dependence on k. This is the property of homogeneity of the Markov chain. Now, let's denote by mu the initial distribution of the process psi k. So mu is the law of psi naught, which means that the probability that psi naught is equal to I is equal to mu of I. Then, using only this relation, it's not difficult to prove that the probability of the path omega naught, omega 1, omega k, when this omega 1, omega 0, omega k are elements of A, the probability of the path is given by this relation. You have initial probability, and you need to multiply by the product of the corresponding transition probability. Everything is described explicitly. Then if you look at this expression, it depends on omega naught, omega k. That is a function on k plus 1 of the direct product on the direct product of k plus 1 copies of A. It is a measure on that space. This is a probability measure on the space. So if you consider all possible values of k, you get sequence of probability measures on the space, on the sequence of spaces A, A squared, and so on. So using the fact that this is a stochastic matrix, which means that if you take the sum with respect to J, respect to the, or you take the sum of every line, you get 1. It's not difficult to understand that what you got here is a consistent family of probability measures. So I denote by omega the set of infinite sequences of elements of A, and by the well-known result, if you have a consistent family of measures, then you can find a measure of mu on this big space whose projection to A to k plus 1 is equal to this measure of mu k for any k. Okay, so given finite state Markov chain, you can define the law of the trajectories, which are elements on this space omega. Now, to simplify everything, I will assume that the process psi k is stationary. And to have only one such a process, or to have uniqueness of its law, I will assume from now on that all the entries of this transition matrix are positive. So I assume that Pij are positive numbers for any I and j. It's not necessary. You can develop everything in much less restrictive hypothesis, but this is for the purpose of this talk, I will assume that Pij are positive for any I and j. Then the Frobenius theorem about matrices with positive entries says that under this hypothesis there is a unique stationary distribution, which means that if your initial state is distributed according to this law mu, then at any other positive time you will have the same law. So we want to study this corresponding measure. We call that given any initial law. The rest is uniquely defined. So we want to study the corresponding path measure associated with this unique stationary distribution of the Markov chain. And our goal is to understand what is the difference between forward and backward evolution. Right? So all this stuff is about forward and backward evolution. So I want to understand what is the difference between the measure mu k, which is the projection of mu to the time interval 0k, and mu k bar, which is the image of mu k and the time reversal, which means that I consider instead of a trajectory omega naught omega k, I consider the reverse trajectory. So I denote by mu k bar the measure on the same space a to k plus 1, which is defined by this formula. To calculate the measure, the probability of trajectory omega naught omega k, I take the reverse trajectory and calculate the probability under mu k. So this is also consistent family on the same space. And I denote by mu bar the corresponding path measure. And I have two measures on the same space omega. The measure which corresponds to the direct evolution, and the measure obtained by time reversal and construction of the measure for the backward evolution. Then you have the following theorem, which is rather well known. It says that these two measures have only two options. Either they are the same or they are singular. So let us remark that these two measures, due to this condition, are always equivalent, in the sense that they are absolutely continuous with respect to each other. So of course it is a very simple situation. You have a measure on a finite space. All these elements are positive, so you have absolute continuity of these two measures. But there is no contradiction. These are two measures on a very large space omega, and they either are the same or they are singular, and they are the same if you have this relation, which is called the tail balance. So you check if this is true, then they are the same. If this is not true, then they are singular. Now let us see how we can describe what else can be said in the situation where they are not the same. Okay, then they are the same, and there's nothing to say. It's the same process. You don't see any difference between forward and backward evolution. So let's see what can be said when they are not the same. To do this, let's introduce what is called the entropy reduction function. So I take the transition from I to j, I divide the transition probability from j to I, and I take the logarithm. So what you get here is called entropy reduction function for the Markov. So why it is called entropy reduction? So how do you motivate this definition of sigma j? Here is the motivation. You take the forward measure and you calculate the density with respect to the backward measure. So this is a function on a to k plus 1. It depends on k plus 1 coordinates. And to make sure that things are easier to write, I take the logarithm. So this delta k is this density. So I take the logarithmic density of this expression. And then using the formula we had for the path measure, remember you had mu omega naught, and then multiplied by the product of these transition probabilities on the corresponding path. So if you do simple calculation, you will get this expression. You have this term, which depends on omega naught and omega k. I will call them boundary terms in what follows, plus a telescopic sum of exactly this functional on the trajectory. You take omega 0, omega 1, you calculate sigma, then omega 1, omega 2, calculate sigma, and so on. So this logarithmic density can be written in this form. Okay, so we call this entropy production. So this is a function which depends on two states. And I denote by sigma bar the mean entropy production. Mean entropy production with respect to direct measure mu1. So what I need to do, I need to take all possible values of I and j, varying a, and then I take the corresponding probabilities under the measure mu. But because we have only dependent on only two states, I can take the projection of that measure to the a squared, and this is exactly the measure mu1. So this is the ensemble average of the entropy production. You can do the same for mu bar. Mu bar is the time reverse measure. If you do the calculation, well, this mu1 bar ij is the same as mu1 ji. But if you interchange these indices, you will get just minus here. So what you get is that if sigma bar is the mean entropy reduction with respect to direct measure, then the mean entropy reduction with respect to reverse measure will be minus sigma bar. And the following theorem gives another description of the two situations I described before. Either they are the same or they are similar. Yeah, yeah, just notation. Sorry, I forgot to mention. This is the mean value of sigma with respect to mu1. Okay, so we have the situation. Let's recall what we had before. We had this situation. Either they are the same or they are singular. They are the same if you have the tail balance. Now we introduce this concept of entropy reduction. The mean entropy reduction with respect to the direct measure and reverse measure are opposite, as they are in the same value but with opposite signs. And the following theorem says that the tail balance holds if and only if the mean entropy reduction is equal to 0. Okay, let us form this theorem. It's not difficult. So we recall that we impose this condition. All transitions are possible. This implies in particular that there is a unique Station distribution. And a little bit more work shows that these two measures, mu and mu bar, these are measures on omega, which is a to z plus. On this space, you can consider the shift map, the left shift. And it's not difficult to prove that both measures will be rewarding. So you have a shift map here. You have two measures. You consider the shift map under the measure mu and mu bar, and it turns out that these two measures are good. Then the Birkhoff-Ergod theorem says that if you take any observable, I take here entropy reduction observable, you take the time average, then ergodicity means that this time average should converge to ensemble average with probability 1. And this is true for both measures, mu and mu bar. Now, if sigma bar, which is the ensemble average of entropy reduction, is different from 0, then here you have two different numbers. Here you have sigma bar, you have sigma bar, minus sigma bar. But on the left-hand side, you have the same quantity. So if you have convergence for probability 1, then these two measures should be concentrated on separate subsets. Because you cannot have on the same set convergence to sigma bar and sigma minus sigma bar. These probabilities are equal to 1. So if sigma bar is different from 0, then the two measures are singular. So let's assume now that sigma bar is equal to 0. We cannot claim immediately that they could be the same, but here is a simple calculation which shows that there is no other option. Let us take this function phi of x, which is x logarithm x, and let's calculate phi of this quantity. We call that delta k. Delta k is the density of mu with respect to mu bar if I restrict them to the time interval 0k. So what is written here is the density of mu with respect to mu bar and integrated with respect to mu bar. Obviously, is equal to 1. And I take phi on 1, I obtain 0. On the other hand, this phi is a convex function. Therefore, if I put this phi under the integral, I will have this inequality. But now, what is phi delta k? It is delta k times logarithm of delta k. Logarithm of delta k here, and delta k times d mu bar is exactly d mu. And what we have here I have to show the formula for logarithm delta k. Here is the formula for logarithm delta k. If I integrate with respect to mu, these two terms will disappear because these are the same term calculated two different instants. And here, each time you have the mean entropy reduction. The process is stationary. It does not depend at which moment of time you calculate the mean entropy reduction. So all this to say that this is equal to k times mean entropy reduction. And I assume that this mean entropy reduction is equal to 0. So we have 0 here, 0 here. Therefore, we must have equality here. But this function phi is strictly convex. And in the Jensen inequality, you have equality if and only if, for a strictly convex function, this delta k is constant. And a simple calculation shows that this can be constant. This constant must be equal to 1 because this integral should be equal to 0. So all densities are identically equal to 1. Therefore, the two measures, projections of two measures on any finite time interval is 0. Therefore, the two measures are the same. Okay, so let me summarize what we have shown so far. You have a finite state Markov chain. For that finite state Markov chain, we introduce the concept of entropy production. We observe that for direct and for backward evolution, the mean entropy production is the same value. The absolute value of mean entropy production is the same, but the signs are opposite. And we derive from here that you have inequality or mean entropy production is equal to 0. You have equality if and only if mean entropy production is equal to 0. So everything is described with the help of mean entropy production. Our goal is study the case when you do have different measures. So from now on, I will assume that mean entropy production is different from 0. Now, the key point of everything is this theorem about large deviations. So let's define the full entropy production as the sum of entropy production on the entire trajectory from 0 to k. Sorry, there is a mistake trace, just double brackets. So let's assume that mean entropy production is positive. Then the theorem says the following. So what is written here, for those who know, this is a large deviation principle for the quantity k minus 1 sigma k, which is the time average of the entropy production. Here is the exact formulation. There is a convex function I, which goes from the real numbers to positive numbers, which may be also plus infinity. It is finite on a symmetric interval around 0, such that the time average of the entropy production, which is exactly this expression divided by k, time is equal to ki divided by k, satisfies the large deviation principle governed by I, and this means the following, roughly speaking. I'm not giving exact definition. Let's consider the probability under the forward evolution that the time average of entropy production is in interval, some interval AB. Right? So we have a probability which is between 0 and 1. I take the logarithm and I divide by k. So what you get, well, first of all, it's not clear why there is a limit. And in fact, there is no limit, but there we can talk about upper and lower limit, but let's keep all this. And roughly speaking, it says that this expression, which is a negative number, is given by the infimum of the rate function on the interval AB. Okay, you have a precise description on the logarithmic scale of the probabilities that mean time average of entropy production is in the interval AB. Or I can write the same thing differently. If I take the exponential, it says that this probability is given by exponential of minus I of r. Of course, I cannot take exactly I, but the small neighbor of r. But let's suppose that I can. Then this is exactly what is written here. This probability can be given by this formula, exponential minus I of r multiplied by the time t. So the limit in general does not. Limit in general does not exist here. But upper and lower limit can be described by the infimum of I on the closed and open interval. Okay, so suppose that this is true. This is a difficult result, so I'm not going to tell anything about the proof. But once you have this, you have the following. And this is the result. I will tell about the history a bit later. This is the result first obtained by Gallavotti-Cohen in the numerical in the deterministic systems. But now I'm talking about the stochastic system. But anyway, the result is the same. And this is the universal character of the law. The rate function, which governs the large deviation principle for the mean entropy production satisfies this universal relation. I to minus r is equal to I of r plus r, and this is true for any r. This function may be infinite, which means that if I of r is infinite, then the other one is also infinite. Now let me give almost a complete proof. Well, it is based on the large deviation principle. Let us recall that the time average of entropy production, which is this, I include this notation because it will be used a few times later. This is basically the density of mu k with respect to the time reversal of mu k. Remember, there were two terms. There was a sum plus boundary term. So let's ignore boundary terms, and let's assume that this time average of the entropy is exactly this expression. The density, well, I forgot here the logarithm. Sorry, I forgot the logarithm, yeah? And I forgot also k minus 1. But anyway, so this is related to the previous formula. So you need to add here 1 over k and logarithm. So let's denote by lambda k and lambda k bar the law of the time average of the entropy on the forward and backward evolution. Then the large deviation principle that I formulated on the previous slide says exactly this. If you are going to calculate lambda k of AB, what is lambda k of AB? This is the probability that time average of the entropy production belongs to AB. Lambda k is the law of this one. So lambda k of LB can be described as exponential minus k, the infimum of I, and this is an asymptotic formula. This is true when k goes to infinity. So let's assume that this is true. This is not exactly true. Well, this is exactly true because this boundary term in this particular model do not play any role. So the large deviation principle says that this is true. Then you have the following two observations. First one says that lambda k gamma is the same as lambda k gamma bar calculated on the set minus gamma. So the probability that the time average of the entropy production belongs to set gamma under forward evolution is the same as the probability that the time average of the entropy production belongs to the symmetric set under backward evolution. Well, this is almost trivial. Let's prove it. So let's denote by theta k the time reversal on the time interval 0 k, which means that you take the trajectory omega naught omega k and you flip it. So mu k bar is the image of mu k under this involution. If you apply it twice, you get the identity. Then for any gamma, I can write what is written here, lambda k of gamma is exactly this. I take the indicator function of gamma, I'll calculate on time average of the entropy, and I integrate with respect to measure mu k. Then, so this is the integral, right? So in the integral, I can make the change of variable roughly. I suppose with theta k, both the function and the measure. In principle, you should write somewhere minus 1, but this is the minus 1 is the same because this is an involution, so I can write theta k here. This one is exactly mu k bar, and using the explicit form of sigma k bar, recall that we said that we assume that this is exactly this. If you compose with theta k, you will get exactly minus sigma k, or I can put minus in the set minus gamma here, and I get the right hand side. So this is the first observation. Lambda k gamma is equal to lambda k bar at minus gamma. Now the second observation is this one. This is a version of Jarzynski. It says that these two measures are absolutely continuous, and the density is given by exponential kr. So let's I emphasize that there is no coefficient here. It's exactly kr, whatever your model, whatever your transition probabilities. To see this, let's calculate the characteristic functions. So phi lambda k alpha is the integral of this exponential with respect to measure lambda k, or I can write the same thing, replacing r by sigma k bar, just transfer theorem for measures. Then I use that mu k is yeah, then I use the fact that mu k is equal to the density multiplied by mu k bar, and this density is exactly this k times sigma k bar. Right? Recall the previous slide. Okay, here it is. This is can be written as exponential of, I forgot the logarithm and I forgot k. But if you add those two terms, you will get exactly this expression that mu k is equal to mu k bar times exponential k sigma k bar. And then you again go back to variable r, you get here lambda k bar, and now you have this integral. And this is exactly the characteristic function of exponential kr times lambda k. So you have this relation. Two measures are absolutely continuous, and the density is given by exponential kr. So once you have this, the rest is very easy. Let's take a small interval around the point r. Then the two observations on the previous slide says that lambda k on the interval is equal to exponential kr lambda k bar on the same interval, because this is the previous formula. And instead of taking this, I can take the same measure lambda k on the symmetric interval, and the symmetric interval is exactly this one. So you have this equal to this one. On the other hand, I have LDP, which says that this probability is essentially exponential minus k the infimum of I. Right? So on the one hand, I have this equality for the probabilities, and this representation that k goes to infinity. Now I take the logarithm here and divide by k. What you get here is on the left hand side is exactly this expression, minus infimum of I over this interval. On the other hand, if you do the same here, you will get here r and a similar expression for this one, minus infimum of I on the symmetric interval. Now this I is a convex function, therefore it is continuous. I pass to the limit when epsilon goes to 0. I get minus I of r is equal to r minus I of minus r. And that's it. This is the same relation as the one written here. So the rate function governing large deviation principle for the mean entropy reduction satisfies this universal law independently of your transition probabilities. Okay. So what is the relation of all this with the second law of thermodynamics about the increase of entropy? So we have proven that for any r, you have these two asymptotic relations, right? The time average of entropy reduction is equal to r, the probability is equal to this one, and the time evolution of entropy reduction is equal to minus r. I'm just writing the same relation replacing r by minus r is equal to this one. Now I divide. Dividing this by this, I divide the second relation by the first one. It gives exponential of the difference, right? Exponential of minus I of minus r, I of r. So this is the ratio of the probabilities of having a negative value, suppose that r is positive, negative value of the mean entropy reduction, of the time average of entropy reduction, and the symmetric positive value. So this is exactly what we want to understand. What is the probability, what is the ratio of probabilities that the time average of entropy reduction has some negative fluctuation compared to the opposite positive fluctuation. So this is exactly this one, but the Gallavotti-Cohen relation says that this is exponential minus rk. And this explains the second law of thermodynamics. This probability, having negative value of entropy, of mean entropy, is exponentially suppressed compared with the probability of the symmetric positive value. Well, a natural question is it possible to develop something similar for more realistic physical models? So the last part of my talk is about fluid flows. But before doing that, let me summarize the program which can be studied for any model, any physical model. Well, I didn't talk much, well, I didn't talk at all about large deviations for empirical measures. I talk about large deviations for observable, but you can study large deviation for empirical measures. Well, this question is interesting by itself, and it's also interesting because of these questions about entropic fluctuations. So it turns out that Gallavotti-Cohen relation has an analog in terms of the rate function governing level 3 large deviations. And the second question you can ask, is that analog, the Gallavotti-Cohen relation, true for the rate function governing level 3 large deviations? So in the first 2 points, you don't have entropy production at all. You just have empirical measures, and you have a property of the rate function governing large deviation for those empirical measures. The next question is about the entropy production. Is there a natural concept of entropy production, and does it mean anything if you want to interpret them in terms of physical concepts? So once you have that, you can ask the question about law of large numbers. Is that true that if you take the time average of entropy production, it will converge to the ensemble average of entropy production? Then, as we saw, the mean entropy production plays a crucial role. If it is 0, then there is no difference. If it is non-zero, then there is there is a difference between forward and backward evolution. So the question you ask is about strict positivity of the entropy production. And finally, large deviation principle for the entropy production, which, as we saw, with some more work, implies the Gallavotti-Cohen relation. So these 6 questions can be asked for any model. You can ask also many other questions, but with these 6 questions are meaningful. And to conclude this introductory part, I'd like to mention that these questions are mostly independent from each other. Of course, A and B are related, and then you have law of large numbers. It is also related to strict positivity, but in principle, you can study them independently. So before going to the last part of my talk, let me mention a few words about the history of the problem. So as I mentioned, the first result about this stuff was obtained by Evans-Searles in 1994 and Gallavotti-Cohen, who discovered the law in numerical experiments and for deterministic systems, or unanswered diffeomorphism, in the work of Gallavotti and Cohen. Then very shortly afterwards, there were a number of work doing the same, studying the same property for stochastic system, by Korchan, Spoon, and Maas, who gave interpretation of Gallavotti-Cohen relation as a Gibbs property. Then there was a series of work by Eckert-Pierre and later by Thomas, who studied the chain of anharmonic oscillators. And there were various aspects of fluctuation relation studied by many other people. Concerning fluid flows and other infinite dimensional systems, probably the first work was by Maesi and Maes, but their work essentially finite dimensional approximation of Navier-Stokes without passing to the limit, which is a different problem. There were a number of work by Bodino, Lefebvre, Barato-Chekrit, and our joint work collaboration with Noé-Cugno. And what I'm going to present now are the results obtained in these 2 papers published in 2015 and mostly 2021. Okay, so here is the model. We study 2-dimensional Navier-Stokes system on the torus. So here you have 3 equations because this U is a vector field. It has 2 components, U1 and U2, and you have also the pressure. U is the velocity field, P is the pressure. So you have here 3 equations for 3 unknown functions, U and P. So the first 2 equations are the equation of motion. The third one is the incompressibility condition for the fluid. So concerning the right-hand side, I don't formulate exact condition for the moment. I just assume that this is a smooth function of t and x, and it is such that is this evolution generates a Markov process. Then, if you impose some non-degeneracy condition on eta, you can prove that this Markov process has a unique stationary distribution, And you can ask the question, exactly the same question as in the case of finite state Markov chain. Is it possible? Oh, sorry. Is it possible to see? I think right. Is it possible to see difference between forward and backward evolution? Now, to make sure that you have a Markov process, let's suppose the following condition. Let's assume that the time axis is divided into intervals of length 1, from k minus 1 to k, and on each interval, you have a forcing e to k which are independent. Right? So this means that you have a time axis. Between 0 and 1, you have the force e to 1. Between 1 and 2, you have the force e to 2, and so on. So these forces, this e to k, they are functions of eta of x and depend also on the random parameter omega. So I regard them as a random variable in this case L2 on the time interval 0, 1 times the torus. And assuming that they are independent ensures that what you get will be Markov process if you restrict it to the integer times. And then I also assume that the mean value with respect to x is equal to 0 to make sure that there is no increase of error. Anyway, so this is not that important. Now, this is more detailed description of what I have just said. If you denote by uk the value of the velocity field at time k, and if you denote by st the resolving operator for the Navier-Stokes system, which takes the initial function v and the right-hand side to the solution time t, then introducing this notation, you can write to find the solution time k, you need to know your solution time k minus 1 and your force between k minus 1 and k. So if you apply the resolving operator to the solution time k minus 1 and the force between k minus 1 and k, you get dk. So what you got here is a Markovian random dynamical system in the standard phase space arising in the theoretic Navier-Stokes system. You need to take the vector fields, the divergence for vector fields, whose mean value is equal to 0 with respect to x. Then under some minor assumption on etk, you can prove the existence and on the more restrictive assumption, uniqueness of a stationary distribution. So you have a Markov chain in this infinite dimensional space, which has a unique stationary distribution. Exactly as in the case of finite state Markov chain, except that the proofs are much more involved. Then you have the right to study stationary trajectory of this Markov chain. Right? You have a random dynamical system. You can even forget that it is Navier-Stokes. You just take a Hilbert space H, and you get this type of random dynamical system. If these E to K are independent, then what you get is a Markov process in this space H. Yeah.
Piecewise constant in time?
No, it's not piecewise constant. It is just a process. I will tell you in a second. It is sorry. It is a function of T and X. It is just in the independent sequence of factors on the interval 0, 1 times T2. Okay, so you have this Markovian random dynamical system. You have a stationary trajectory. As in the case of finite state Markov chain, you study the law of finite segments of finite. So this mu k is exactly the same object as in the case of finite state Markov chain. You study the trajectory between the times 0 and k, and denote by L the distribution of the trajectory, log the trajectory. Now, in contrast to finite state Markov chain, there is a big problem here. There is no reason for this measure mu k be equivalent or even absolutely continuous with respect to its time reversal, unless you impose very strict condition on this E to K, which are not physically justified. Then you need to do something. You still want to study the problem. So there are several options. The first one is to do finite dimensional approximation. When you do finite dimensional approximation, then under some reasonable conditions, you can prove that the trajectories are at equivalent laws. And this was done, well, maybe not rigorously, but still in this work, they describe the entire procedure. However, passing to the limit is not easy. For instance, it can be proven that for finite dimensional approximation on your system, you do have large deviation principle on level 3. And you also have large deviation principle on level 3 for the full Markov system, for the full Navier-Stokes system. But it's not known if the two rate function converges to each other. If the finite dimensional approximation, it has a rate function depending on n, if it converges in some sense to the rate function of corresponding level 3 LDP for the full system. So this is to say that passing to the limit in this object are not obvious. Another option is what I mentioned before. You need to assume very strict hypothesis on the dynamics. Basically, you need to assume very strong dissipation and roughness of the noise, which means that it should be irregular with respect to x. Then, in some cases, the program can be carried out, and this was done by in our joint work in 2015 for the Berger situation. But the roughness condition is not very physical. Another option in this context is to place a particle in the fluid flow, and instead of studying the whole flow, you study the evolution of the particle. And this is what was done in our work in 2021. So we take a stationary solution of the Navier-Stokes system. It is a time-dependent random field on the torus, right? So u is a function of t and x. T is time x belongs to t2, and it depends on omega. So you have a time-dependent random field, and you place a particle in that random field. In other words, you study the evolution defined by this ordinary differential equation with random field u t x. So we assume enough regularity with respect to t and x so that the evolution for this ordinary differential equation is well defined. And the question is if you can carry out the program of this consisting of those 6 points for this program. To do that, we need to impose some condition of k. Now let me briefly mention what is written here. You take an orthonormal basis in this case L2 on the time interval with range in age. H is the space, is the phase space of the evolution. Eta is acting on the right hand side, so it is in the same space. So you take a orthonormal basis here, and you assume that each eta k, so we call that eta k is the force on the interval k minus 1k. So you assume that this eta k can be expanded in this basis, expansion in this basis, and here psi jk are independent random variables, and bj are some numbers going to 0 sufficient to pass, so that there is no problem with the convergence of the series. And concerning psi jk, I assume that they have smooth flows, smooth densities with respect to Meg measure. They are supported in -1, 1, and are positive in the small neighborhood of 0, which means that with positive probability, this eta k will be very small. Now, this ensures that the Navier-Stokes system has a unique stationary distribution. So we are very close to the situation we studied in the case of finite state Markov chain. And this time-dependent stationary random field is well defined. Now, what can be said? And here is what you can say. There is a random process taking values on the torus. So we are talking about the particle moving on the torus. So there is a random process taking values on T2 whose trajectories satisfy these 4 disorderly differential equations. The 4 is disorderly differential equation. Okay, so you can construct a stationary solution of this ordinary differential equation, but it's not stationary for all time because your noise is not stationary, so there is no reason for this one to be stationary. But if you take the restriction only to the time, then you get a stationary process. So in that sense, you have a stationary process. Then you take any initial condition P on the torus and consider corresponding trajectory of the particle, which is moving in this random time-dependent vector field. And then you consider finite segment of trajectories. y t is the trajectory time t, you fix s, and you consider segment of length s. Y time k, k plus 1, k plus s. So you have a random variable in t2 to the power k plus 1. And the second point says that this, independently of the initial condition, this will converge in total variation norm to the law of this station process. This again similar to the finite state Markov chain, right? You have a, due to the law of probability, you have a unique station distribution and you have convergence. And finally, you have level 3 large deviation, which means that you take Dirac mass of the full trajectory, full forward trajectory. You take the empirical measure. What you get is a measure here, right? This is a random variable between here, so this is a measure on that space. So this quantity, this random variable here, satisfies the large deviation principle with a good rate function. So you do have large deviation principle, but not for entropy production. For the moment, it's about level 3 large deviation. So what else can be said here? Here's the second point. It's about entropy production. Well, to do that, I add a parameter in front of the eta. Yeah, here it should be eta k. Right, so this is the force time interval k minus 1k. So I added a parameter here. In the second part of the theorem, it will be large. Remember you had a stationary process, which attracts all other trajectories with exponential rate. The first part of the theorem says that this random variable, which is a random variable here, has a smooth density with respect to the vector. Moreover, if this A is sufficiently large, then this density is strictly positive. So that you can define what we did for finite state Markov chain. We took density on the forward trajectory and on the backward trajectory and took the logarithm. So if the density is positive, you can define the logarithmic density. And what you get, we call it entropy production by analogy with the finite state Markov chain. What you can say is this one. This quantity is bounded from above and from below. Unfortunately, this is all what we can say. We cannot say more at the moment. So the remaining 4 questions remain open. So let me remind those 4 questions. You have level 3 fluctuation relation. This is a relation for the rate function governing large deviation principle. So you have a rate function here. You can define an analog of Gallavotti-Cohen relation for this rate function, and question is it satisfied for this model? You can ask about the mean entropy production. We call that the entropy production is defined, but we don't know if there is a limit of this one, of this quantity, as k goes to infinity. So we don't know if the law of large number is true. Third question, you have about the strict positivity of the ensemble average of entropy production. And finally, large deviation principle of the entropy production, which would imply Gallavotti-Cohen. I think that's all what I want to say. Thanks for your time.